Hello, everyone. So today I'm going to go over tolerancing. It's a really important topic that we talk about and that we use constantly in design and industry. So this is very important that you all take notes and listen to what I stress. There will be questions on the final exam about this, and there will be questions on the quarterly and the midterm. So let's take a look at tolerancing today. Tolerance is variation. Variation is unavoidable. It is the amount of play or the amount of room that you have in parts that are manufactured. There's always going to be some type of variation. Tolerances are used, in drawings to control the manufacturing process, so we make sure that pieces and parts fit together. Tolerancing is used very much in mating parts, where we mate various different parts together and we put various different things together to make sure that going from one part to another or one assembly to another, that they're going to be interchangeable and that there won't be any problems with the mating. Large tolerances are big. When we have large tolerances, there are things that go on with that it can make things very sloppy. If we have a large tolerance, let's say on an engine or on a bearing, if there's a large tolerance on a bearing, we're going to get rattling and shaking because there's going to be movement in there. If we have a large tolerance in a piston, then the fuel will leak down into the oil pan, into the oil reservoir, and thin out the oil because gasoline is a solvent. Small tolerances, on the other hand, are going to affect the cost because a smaller tolerance, something that is very, very tight as far as the tolerance is concerned, is going to take longer to do and going to take more skill to do. So it's going to have two negative effects on the manufacturing process. One, it's going to take longer, and two, because time is money, it's going to make it more expensive. So don't specify a tolerance that is smaller than what's necessary. ANSI, ASME, ISO, the International Standards Organization, all of those, have tolerances that are expected for certain things. Those tolerances can be identified as reference, max, maximum, minimum, or stock. Now, to understand what stock is something that you buy right off the shelf or you buy directly from a company. You can go out and you can buy 1-inch round dowel rod off the shelf. You can buy a 2x4 off the shelf, but you can't buy a dowel rod that is 13/16. They don't make it, so you have to have it either custom made or you have to have it turned down on a lathe to make it the size that you need. Okay, so tolerances are applied directly to the dimension, or they can be a general note like we did in our puzzle project where we put plus or minus 5/1000 of an inch in the title block. Now this is an Arbor Press. And so an Arbor Press, what it does, it actually squeezes things together. This handle is a lever, as you know, from POE. This handle has to slide up and down. And what it does is it applies pressure through this arm here. And what it does is it can squeeze things together that aren't necessarily the size. Let's take, for instance, this handle, this knob that's on the handle. So the knob, we drill the hole actually smaller than the handle diameter. Yes, smaller. And yes, steel has elasticity. If you don't believe me, just sit on a bridge on a highway and if you get stuck in traffic and on the other side the traffic's moving, you can feel a semi truck shaking that bridge. So that bridge has flexibility. That steel has flexibility. So this can stretch out. And what we do is we use a press like this or similar to this to press that ball on there. Now, why can't we just make it out of one solid piece? Well, because we have to slide this handle through that hole and it has to slide back and forth. All of you have seen vices in our shop, and that's what happens with the handle. It slides back and forth. They just put the end on of the vices on a little bit different than what's here. So variation and tolerance affect the functionality. This piece has to slide up and down through this slot. That slot can't be smaller than this piece right here, like we did with the knob on this handle. Okay, this this shaft right here has to spin around inside this hole, and so on. So it depends on the functionality. All right, let's take a little bit more look at this. So there's three basic types of tolerances that occur most often in work and drawings. The first type is a limit dimension. There's no targeted dimension, there's no specified dimension. It is strictly a limit. You can be this big or this small, anything in between is fine. And a lot of times it just has something to do with things that aren't really super important. Because a handle goes in here, there's probably a lot of play that goes on the other side. It's probably bolted on the other side. So this thickness doesn't really have a lot of effect on how this particular press works. All right, so that's a limit dimension. Can be 975 thousandths small or 980 thousandths big or anything in between, and it's okay. The second type is a bilateral tolerance. Now here we have a specified dimension. So this is a counterboard hole. There's a hole in here that's a 1/2 inch diameter, and this is counterboard, not all the way through right here. So this 1.170 hole here is the counterbore. So it's bigger than that 1/2 inch hole. And then that counterbore goes down 776 thousandths of an inch. So here we're saying that the diameter of this counterbore right here can be, the targeted dimension is 1.170 plus or minus 2 thousandths of an inch. So that means you have a total amount of tolerance of 4 thousandths of an inch, because it can be 1.172 or it can be 1.68. Okay, which is a total difference of 4 thousandths of an inch. All right, so that's bilateral. The final one is unilateral. So it can only go one direction. We still use the plus and the minus, but one of them will be at 0 and the other will be bigger. So in this particular case here, what they're saying is that it's in an ideal situation, it would be a 1/2 of an inch, 500 thousandths of an inch, which is a 1/2 an inch. But it can't get any smaller, because if it gets smaller, if we go back up to here, this shaft, the probably maximum of this shaft is probably 499 thousandths, so just under a 1/2 an inch, right? So if this gets any smaller, then that shaft that goes up and down through here is not going to work. It's going to stick, and you're not going to have the functionality of the press. So those are the three different types of tolerances. Now here, this is a keyway right here, and you'll see this a lot on the bottom of mowers or on a shaft where there's a pulley, maybe some type of electric motor that has a pulley that maybe works a pump or something of that sort. And what they do is they cut this keyway through here, and they cut the keyway through the other side, and they very tightly fit a square key in there to hold those two in place so they won't spin around. Okay, so here you can see that this limit dimension is 1 thousandths of an inch. That's really small. Think about that. Your hair is 3 thousandths of an inch thick on average, right? So you're talking about 1/3 of your hair is how much that manufacturer has to be within. All right, so limit dimensions provide an upper and a lower limit for the dimension, and you can see any size in between is okay. And here you can see that we're only talking about 1 thousandths of an inch, because the upper limit is 126 thousandths and the lower limit is 125 thousandths. All right, so bilateral tolerance, let's take a look at this a little bit more. So bilateral, when we take a look at the depth of this counterbore here, okay, so this is that piece where we had that counterbore. This is talking about the depth, and now they're saying that the depth, what we want on the depth, that's a symbol for depth, how deep you go with a hole, okay, is plus or minus 3 thousandths of an inch. So it can be bigger or it can be smaller, but it can't, in a perfect world, it would be 1/4 of an inch or 250 thousandths of an inch, right? So the counterbore depth can be 3 thousandths larger or 3 thousandths smaller, okay? But the ideal is 250 thousandths. Okay, now here, when we take a look at it, so from the datum here to the center of that hole, it can be plus or minus 50 thousandths of an inch or 500ths of an inch here. Now this is significant. We cannot round any of these things off because they are significant digits. All right, unilateral tolerance. So here what they're saying with this counterbore is that it can get bigger by 4 thousandths of an inch, but don't make it any smaller because we've got a shaft that's going to go in there, and the shaft is probably just smaller than 1/2 of an inch for its maximum size, okay? So therefore, we don't want that hole, that counterbore, to get any smaller there. So bilateral tolerance provides an equal allowable variation, larger or smaller, and it uses a plus or minus symbol. And I think I just went the wrong direction here. All right, so we use a plus and minus again, and the hole diameter can be, we have a total variation of 4 thousandths of an inch, but don't make it any smaller than that 1/2 inch. All right, so when we take a look at this, I want you to just stop for a second here, take a look, and tell me what kind of tolerance this first one is. If you said unilateral tolerance, you would be correct because it only can get bigger, but it can't get smaller. All right, think about what this one is going to be and take a look at this. What type of tolerance is this in the red right here? And if you said bilateral tolerance, you would be correct, right? Because it's got a plus minus 2 thousandths of an inch each way. Finally, down here, what is this tolerance down here? What type? If you said limit dimension, then you are correct. All right, so let's continue on here. Specified dimension, that is in a perfect world what the dimension would be if there wasn't any variation. Okay, a lot of our machinists are very, very good. They can get really super accurate, but again, sometimes accuracy is not a positive thing because it costs too much or it just makes things too time consuming. All right, let's look here at definitions. So limits are the maximum and minimum size shown by a tolerance dimension, okay? So in this case, we have plus or minus 50 thousandths or 500ths of an inch. So if we add 500ths of an inch to the specified dimension, we're going to get an upper limit of 155. If we subtract 500ths from the 1.5, we're going to get 1 and 4500ths, okay? So that's upper limit and lower limit. Now, what difference does that make? Well, it gives us a complete and total tolerance. So if we subtract the upper limit and the lower limit, we subtract the lower limit from the upper limit, we're going to get a total tolerance of 10 hundredths of an inch or 100 thousandths for the total tolerance, okay, which is actually pretty sloppy in today's manufacturing. All right, let's take a look at this calculating tolerance. It's really very simple. We have the 150 here. Okay, we know that we can be bigger by 500ths of an inch. So the upper limit being 155. We know we can be smaller by 500ths of an inch. So that's 145 for your lower limit. So when we take these two and we add those together, we're going to get a total tolerance of 10 hundredths of an inch. That will be on the exam. All right, in the absence of any tolerance, there are default tolerances. So if there's no general tolerance, if there's no specified tolerance, then we go to, how many decimal points are there? So right here, the angle would be 1/2 of a degree. So plus or minus 1/2 of a degree would be the angle. If we have a 1/10 of an inch, if all our decimals are at 1/10 of an inch, then it would be plus or minus 20 thousandths of an inch. If we have 2 decimal places, then our default tolerance is plus or minus 10 thousandths of an inch. And if our default, if we have 3 decimal places and we don't have anything specified, it is defaulted to plus or minus 5 thousandths of an inch. So our total tolerance here be 40 thousandths. Our total tolerance here is 20 thousandths, and our total tolerance here is 10 thousandths, because remember, we're going plus and minus, we're going in both directions. All right, general tolerances. So we take a look at this. All right, what is the general tolerance of this 3 right here? It's 2 decimal places. If we look at the chart, it means it's plus or minus 10 thousandths of an inch. Okay, and that goes with all of these down here because they don't have a tolerance specified for them. So therefore, it would be plus or minus 10 thousandths of an inch. Okay, upper limit, lower limit. And that's what gives you a total tolerance of 10 hundredths of an inch. All right, so there are different types of fit. Now, there is a clearance fit, an interference fit, and a transition fit. Well, what does that mean? Well, I want you to think about your Tonka truck or your Barbie or Ken Safari Jeep and how the wheels are put on the axle on those. Okay, they are squeezed on. Now, that's an interference fit. When they get squeezed on like that, that's an interference fit. There always should be an interference fit for them to stick together and to hold on together. But a clearance fit is the axle that goes through the hole where it allows the axle to spin around. So that's a clearance fit. Another example of an interference fit would be the hammer handle going on the hammer head. You always want that hammer head or the axe head to stay on that handle, because if not, that thing's going to be coming flying off and it's going to hurt somebody. So that's an example of an interference fit. Now, a transition fit is one that occurs with too many parts. Sometimes it can have a clearance fit, sometimes it can have an interference fit. Think about your puzzle, okay? Some of your puzzle parts probably went together really clean and smooth and didn't have any interference whatsoever. Some of them, you probably had to sort of squeeze them together a little bit. And so either one, that's a transition fit, okay? So, all right, clearance fit. If we take a look at the maximum material here, okay, no matter how big we make this shaft and how small we make this hole within the tolerance, okay, we're going to see that there's always going to be a clearance fit. Okay, an interference fit, no matter how small we make this shaft and how big we make this hole, there's always going to be an interference. All right, so this is maximum material condition, is what we call maximum material and minimum material condition. So let's take a look at that and how we can calculate that. Least material condition, maximum material condition, okay, and let me just explain that in here. Okay, so that is going to define our allowance. The allowance is the minimum clearance or maximum interference for a clearance fit. Now, this is on the exam, I guarantee you. So make sure that you understand how to do this. All right, allowance, we're going to take the maximum material condition and we're going to take the minimum material and of the external, the maximum material of the external and the maximum material of the internal, and we're going to subtract those two together. So here, if we take a look at this and our maximum material on this shaft is 10 and our maximum material is actually smaller on this hole. Now, this is where Project Lead the Way, when they ask this question, this is where they're going to get you. If your maximum material here is, it's a smaller hole, right? Because that means you're going to have more material. Don't get fooled by taking the bigger dimension here. All right, so we're going to take 10.15, we're going to subtract 10, and we're going to get a positive 15. Now, whenever we have a positive number, that means that there's going to be what type of fit? A clearance fit, yes. It's going to be a clearance fit, okay? So maximum material condition of the hole, since it's smaller, will result in more material, right? And maximum material of the axle is going to be a larger part, okay? So don't get yourself fooled in here, all right? So in this case, maximum material featured is going to be 10, then maximum internal is going to be 988, right? So when we take that, we're going to have a negative number, because what's going to happen is that we're going to have this piece is always going to have an interference. So when you have a negative number, there's always going to be an interference fit. Okay? All right. Note about dimensioning tolerance. In general, the more specific the dimension, the tighter the tolerance. Over precise dimensions or overly tight tolerances increases the manufacturing cost. Time is money, right? Specify dimensions on only to the precision and tolerance that are necessary to the part to function properly. All right, so that's really what Project Lead the Way wanted you to talk about. I'm going to add some other things here. There's geometric tolerancing. And geometric tolerancing means that there's certain things that have to happen to make a product work properly. In this case, this table needs to have a flatness to it. Maybe it's a very precise table where they're measuring precise things on it, okay? So what we do is we put a feature control box in, and this feature control box says, hey, there's a symbol right here, and it says this tabletop needs to be flat within 50 hundredths of an inch. So they need to make it a little bit smoother, okay? So that entire area there is very important. Right? These are the symbols that are important to us. Now, you're not going to see all of these. I will mention a couple of them. You're going to be putting datum on yours. Yeah, you'll be putting, some other ones. Flatness is important. All of these are actually important, but cylindricity is important. Parallelism can be important. All of these can be important, but you will see certain things in there that are probably more to what you can understand than others. Okay, perpendicularity. There is countersink and how that should be. Angularity, run out and run out total, and that's how something goes out. Counterbore, spot face, and how that has to be done. Slope, you guys have seen that. And so there's all these different symbols that can be put into this feature control frame. And yes, Inventor has a feature control frame on how to do that. Okay. Primary datum. The primary datum is selected to provide a function of relationship and accessibility to repeatability. In other words, we want the very best side to measure from. You can't measure from a tangent very well. You can't measure from an edge very well. You can't measure from a curve very well. So it's really important that you get a good datum. Where are we going to measure from each and every time so that we can make sure that it is as precise as we need it to be? Think about that, right? Think about that. Think about some of your parts that you did for your puzzle piece and how important it is for them to measure from a certain area. All right. So if we take a look at this object right here, it's in its natural resting position like this. Here's the front view, natural resting position. That is a good flat surface, which means it's a good surface to measure off of. So therefore, what we're going to do is we're going to call this out as being datum A. So that's the most important surface. Okay. So we also have secondary and tertiary datums. The secondary being, a product perpendicular to the primary datum, so it can be measured and referenced from them. And the tertiary, the datum that's always perpendicular to both the primary and secondary datums to ensure that those fixed relationships from those parts, right? So here's our primary, here's our secondary right here. So we have a secondary one that's perpendicular to A to make sure that is square, and then perpendicular to that, perpendicular to plane A and to plane B is the tertiary. So there's our tertiary plane from there. So you can see how that works. All right, example of feature controls. So here's an example of parallelism. Maybe this thing is running in, spinning around, the shaft is spinning around inside of something. And so if it is angled at all on this edge or angled at all on this edge, one of those edges is going to score the inside of whatever it is. So it may be very important that these two sides are extremely parallel to one another. It may be important that the cylindricity of this particular shaft has to be extremely round. Okay, so this might be something that, again, may be very important. All right, so you can see how that works and how we can add those into there. So parallel by 1/100 of an inch from datum A. All right, so here we're just talking about how round this needs to be and how important it is for that to be round. So you can see a shaft and a bearing here and how important those things it might be that if the bearing and the shaft aren't extremely round, that we could get a lot of juggling in there and we could get a lot of issues as far as this thing starting to shake and rattle and roll, right? So we don't want necessarily that to happen. Okay, this flatness, again, might be very important. Now, these are called break lines right here. This may be a very long shaft, and they just broke this apart to let you know that they showed those symbols right in there to show you that it's actually drawn shorter than what it really is. But this is for your flatness, your straightness rather, and how straight this should be according to when it's run out. Okay, so it's very important for that to be very, very flat there. Okay. All right, so terminology review, maximum material condition, where the size features the maximum amount of material. Okay, least material condition, where it is the least amount that's there. Tolerance, the difference between MMC, maximum material condition, and the least material condition of a single dimension. Okay, allowance, the difference between the maximum material condition of the two mating parts. Okay, and basic dimension is just a nominal dimension for which tolerances are derived. And feature controls, this is your geometric symbol, your tolerancing information, and these are your datum references, datum A, datum B, datum C. Okay, so connecting with the words within the features, that all works to what our tolerances is. All right, I hope you enjoyed that, or at least got something out of it, and we will continue on with some more videos later.